Hey guys, so in this video I'm just going to quickly walk you through what happens to the lift distribution, or more specifically the lift as a function of angle of attack for a finite wing. So in the last class we talked about the lift distribution and how to predict downwash, induced angle of attack, and induced drag coefficient for a given lift distribution. But we didn't quite specifically talk about what happens to lift as a function of angle of attack, right, for a finite wing. So in this short video, I'm just gonna go over some of the steps involved in doing that. And if you listen to it, it's very simple to understand. So we will talk about this in the next class. But since you guys are doing the homework, I thought you might appreciate this information. And you must have seen this equation a lot, when you took intro to flight or some other way. But again, you must have seen it somewhere. So this is just the origin or the derivation of that equation. So let's get right to it. The lift curve slope on a finite wing, or the lift curve slope for an airfoil, and using thin airfoil theory, what we got was dCl by d alpha was 2 pi, right? So we derived this equation in thin airfoil theory, and it's the same for symmetric and cambered airfoil, right? So that's good. So let's look at how this changes for a finite wing, okay? So when you look at the diagram, I think figure 4 in the last handout, so the lift depends on effective angle of attack, right? Because you have an induced angle of attack, the geometric angle of attack is not the angle of attack is producing lift, but it's the effective angle of attack, right? So it's only right to say that in a dCl by d alpha effective, which can be written as in alpha minus alpha I. This is a relation between geometric effective and induced, right? So that's equal to 2 pi, right? So we're specifically just substituting a geometric angle of attack to an effective angle of attack, and writing effective angle of attack in terms of this, right? So let's integrate the equation above. So you integrate dCl by d alpha minus alpha I in 2 pi. Once you bring this to the other side, when you integrate it, you'll just see Cl is 2 pi times alpha minus alpha I, right? So, from lifting line theory, we actually proved that this alpha I is Cl by pi AR. So that's kind of what we talked about last time, right? So again, this is for an elliptical lift distribution, right? So you don't have that span efficiency E, but you'll see that will come later, right? So it's 2 pi geometric angle of attack minus induced angle of attack, right? Now let's multiply that, or sorry, so let's differentiate that with respect to alpha, and you will get this, right? So dCl by d alpha, 2 pi alpha will become just 2 pi, and 2 pi times this term here will just be, the same terms, but you have Cl, so you have to differentiate that with respect to alpha, right? So you have 2 pi minus 2 pi by pi AR times dCl by d alpha, right? Now when you solve for alpha, so bring this term to the other side, take dCl by d alpha as common, and then bring the denominator, bring the multiplication term down below, and when you solve for dCl by d alpha, you pretty much get this equation, right? So dCl by d alpha is a lift curve slope for a 3D wing that is equal to lift curve slope of a 2D wing, which is 2 pi, divided by 1 plus 2 pi, which is again the lift curve slope of the airfoil, divided by pi AR, right? That's it, right? So that's the lift curve slope. So what can you, now in the next class, we can talk about what happens to the lift curve slope as the aspect ratio increases or decreases, right? So again, this is for a wing with elliptical lift distribution, but for a general lift distribution, you have the same equation, except you have this 1 plus delta, again, the induced drag factor, which we talked about in the last class, right? So, and using the span efficiency formula, which is span efficiency is 1 by 1 plus delta, you can write this equation as 2 pi by 1 plus 2 pi by pi EAR, right? So this equation is nothing, here's span efficiency, and this equation is called Helmholtz equation. right? So basically, there are two ways of finding span efficiency. You can actually find through induced drag coefficient for an equation that we talked about in the last class, or you can use this equation, right? Because all you need to do is figure out what your lift curve slope for the 3D finite wing is, and you know the aspect ratio, you know everything else, and you can solve for E, right? Pretty simple as that. So, we'll talk about this next class, but pretty much what this equation says is that as the aspect ratio decreases, your slope actually decreases. Again, because your aspect ratio decreases, you have, most of the area will be covered by the wingtip vortex, which is not a straight flow feature, right? The wingtip vortex is more like tornado-like structure, which decreases the overall lift produced by the finite wing. And that's why if you look at a given angle of attack, a higher aspect ratio one produces more lift than the lower aspect ratio one. Again, we are not talking about the area, okay? Aspect ratio is b squared over s, right? So don't think of as, hey, a smaller wing can also have higher aspect ratio, right? Because, if it has a smaller chord, things like that, right? So it's the aspect ratio that matters, not essentially the span alone, okay? So that's kind of what I wanted to talk about in this equation, in this figure. Again, here is another diagram for 3D wing. Especially what this says is that the lift curve slope of an airfoil is the highest you can get. I mean, you can increase that by using flaps per se, but theoretically, lift from an airfoil is the highest lift that you can get from that airfoil, and the 3D wing will always be lower than the airfoil. If you get something higher, then you're doing something wrong. So that's kind of what I wanted to discuss. Now you guys know what Helmholtz equation is, and we'll definitely talk about that in our last class. But you have this information, so you should be able to calculate E. You can also calculate E using induced drag equation that we saw earlier. All right, guys. See you tomorrow.